Okay, so let's look at number 1 here. We have to prove that this is an equivalence relation. So E is the relation defined on the integers as follows. For all m and n in the integers, m is related to n by E if and only if 2 divides m minus n. Okay, so let's go through the things we need to prove here. So the first one is we have to prove that this is reflexive. Okay, so that means that every element is related to itself. Okay, so what we're going to do is we're going to take an element from the set that this relation is on. So I'll just call it M. So let M be in Z, and we need to show, you don't have to write this in yours, but we need to show that M is related to itself by E, like this. Okay, so let's see, what do we know about M? So I need to show that M minus M is divisible by 2. So M minus M is 0. And 0 is divisible by 2 because it equals 2 times 0, which is an integer. So this is true. M is related to itself by E. All right, so that was pretty easy. Now let's do the symmetric property. So symmetric, I'm going to need to take 2 elements from the underlying set. So I'll call them M and N. And what we're going to do is, well, let me show it like this. So we will show that if M is related by E to N, then N is related by E to M in the other order, like that. So we're trying to show an if-then statement. That means we're going to need to do a direct proof. So I'm going to assume the if part, and then I'm going to show the then part. So let's suppose that M is related to N by E. All right, and what do I get from that supposition? So that supposition tells me that means that 2 divides m minus n. Okay, so that means that m minus n equals a multiple of 2. I'll say it equals 2 times k for some integer k. This is just the same as saying there exists some k such that m minus n equals 2k. Okay, so then what is n minus m? So then n minus m, isn't that just the negative of m minus n? So isn't this just negative 2k? Or in other words, 2 times negative k? All right, then since negative k is also an integer, this shows that 2 divides n minus m. So n is related by E to m in the opposite order, like that. Okay, so this does have the symmetric property. And then finally we need to show the transitive property. So for this one I need 3 letters, so I'm going to let m, n, and I don't know, l be in the integers. Okay, and now we will show the following. So we will show that, and again, you can leave this parentheses part out, but I'm just trying to give you the idea of what we're going to do here. So if m is related to n by E, and m is related, oh, sorry, not m. If n is related by E to L, then we can sort of transit between m and L along that little chain there. So m would be related by E to L, like that. So that's what we need to show, and it's an if-then statement, so we're going to do it with a direct proof. So we'll assume or suppose or let m be related to n by E, and n be related by E to L, and then we're going to try to show that m is related to L by E. So what do we get from this assumption here? Okay, this means that 2 divides m minus n, and also 2 divides n minus L. Okay, so, well, what can we do then? If these are both divisible by 2, then m minus n equals 2 times k for some integer k. And likewise, for the other one, n minus L equals, I have to use a different letter now, so I'll call it I. 2 times I for some I integer. Okay, Now how am I going to get m minus L? So I think I can actually just add those two equations together and get m minus L. So m minus n plus n minus L equals m minus L. So m minus L is going to equal 2k plus 2I, right? That's what I get from adding those two together. Okay, and that is going to be a multiple of 2 because I can just factor a 2 out of it. So now I just need to argue that that means that 2 divides m minus L. So since k plus I is an integer, this means 2 divides m minus L. So m is related by e to L. All right, and that's what I needed to show. So at this point, I've shown all three properties and I'm done. Okay, let's look at another one. This one is actually quite similar. So C is the relation defined on the integers as follows. For all a and b in the integers, a is related to b by c, if and only if 5 divides a cubed minus b cubed. Okay, so let's go ahead and start with the reflexive property. So for reflexive, I'm going to take one element in the underlying set. So let A be an element of C, and then I'm going to show that A is related to itself. So in order to do that, I'm plugging it into the definition there for both A and B. So I need to show a cubed minus a cubed is divisible by 5. So that is not very hard because a cubed minus a cubed is 0, and 5 does divide 0. All the integers divide 0. So this means that A is related to itself by C. Okay, so that's reflexive. And now the symmetric property. So for this one, I need to let there be two integers. So I'll call them A and B. And I'm going to suppose that they are related to each other in the first order. So suppose A is related to B by C like that. And then I'm going to show that B is also related by C to A. So this assumption here means that 5 divides a cubed minus b cubed, like that. Okay, so a cubed minus b cubed equals 5 times some integer, which I'll just call I, where I is an integer. I should have said some I and z. Let me just erase it. Putting the for some I and z part at the end there is the same as putting then there exists some I and z at the beginning. Yeah, so then what is b cubed minus a cubed? So that's what I need to find in order to show that b is related to a by c. Okay, so then b cubed minus a cubed is just going to be negative 5i, or I can take a 5 out of that and put the negative I in parentheses. Okay, and then I can say that since negative I is an integer, this shows that 5 divides b cubed minus a cubed. So that means that b is related by c to a. Okay, so that's the symmetric property. And then for the transitive property, you need to take 3 elements. So I'll call them well, I don't really want to use C because I'm already using C for something else, and I don't think I can write it differently enough, so I'm going to call them A, B, and D. So let A, B, and D be in the integers. And now I'm going to suppose that A is related to B and that B is related to D. So A is related by C to B, and that's not a D, sorry. And B is related by C to D. And I'm going to try to show that A is related to D. Okay, so since A is related to B, that means that 5 divides a cubed minus b cubed. So there exists some integer, which I'll just call k, I guess. So there exists some integer k such that a cubed minus b cubed equals 5k. And then I'll do the same thing for the relationship between b and c. So since b is related to d by c, there exists some integer, which I'll just call j, I guess, such that b cubed minus d cubed equals 5 times j. Okay, so that's what it means to be divisible by 5. Oops, I left that part out, didn't I? Sorry, I skipped right to the end of it. Let me go back. Oops. Okay, so that means, okay, so since b is related to d by c, that means that 5 divides b cubed minus d cubed, and then that means, so there exists some integer, which I'll call j, such that b cubed minus d cubed equals 5j. I mean, you could just skip right to that, it's fine, but I just wanted to put in the intermediate part so you understand it better, I hope. Okay, so then how are we going to get a cubed minus d cubed? So again, we can just add the equations together. So then by adding the equations, we get a cubed minus b cubed plus b cubed minus d cubed is going to equal 5k plus 5j. So here the b cubed and the negative b cubed cancel out. And then we can also factor out a 5 here to get k plus j. Okay, so since k plus j is an integer, this shows that 5 divides a cubed minus d cubed. So that means that a is related by c to d, and that's what we needed to show for the transitive property. Okay, so that one's done. All right, let's look at the last one. So this time the elements in our set are ordered pairs, so it's a little bit tricky maybe. And then the thing that is making two ordered pairs equivalent is if their first coordinates are the same. All right, so let's give this a try. So first for reflexive, I'm going to take one element from the underlying set, but remember the underlying set here is r cross r, so my element is going to look like an ordered pair. So I'm going to say let wx be in r cross r. Okay, then I'm going to show that wx is related to itself. So how am I going to do that? I want to show that w that has the same coordinate, wx and wx have the same first coordinate is what I'm trying to say. So then w equals w, so w comma x will be related by L to w comma x. So it's not very hard, it's pretty obvious. All right, let's do the symmetric one. Okay, so now I'm going to take two ordered pairs. So I'm going to let wx and yz be in the reals cross the reals. So that's all ordered pairs of real numbers. And now I'm going to suppose that these two are related to each other by L. So I'm going to suppose that wx is related by L to x, or sorry, to yz. Okay, and now I want to try to show it in the other order so that yz is related to wx. So what do I get from this supposition? Then this tells me that w must equal y. Well, since w equals y, y also equals w, so I can just do these in the other order. So I can put the yz here and then put the wx on the other side. Okay, so that was pretty easy. And then finally, let's do the transitive. So I'm going to need three ordered pairs this time. So let's see, I'll do, I guess I'll start with uv, and then wx, and then yz. So they're all in alphabetical order. Okay, and now we're going to suppose that these are all related in a little chain. So uv is related to wx, and wx is related to yz. Okay, so then what do I have? So uv is related to wx, that means that u has to equal w, and wx is related to yz, so that means that w has to equal y. So then I can use the transitive property of equality to say that u must equal y. So then from there I can say that uv is related to yz, which is what I need for transitivity. So actually this one was the easiest one, even though it's a little bit complicated with the ordered pairs. So all you're going to have to do on these questions is just draw a Hasse diagram. So the partial order here is, we're giving it by this little symbol here, the less than or equal curvy symbol. So the underlying set that we're going to do our Hasse diagram from is these subsets here, and the partial order relation is actually the subset relation. So we're just going to put the one that is a subset of most of the other ones at the bottom, and I think the empty set is a subset of everything, right? So that is going to go at the bottom. And then the next thing, what is something that contains that as a subset and doesn't contain any of the others? So it makes sense to go just to the next smallest set. So if I have the set just containing A, that will contain the empty set as a subset. So I'm going to have an arrow that goes up from the empty set to that set that just contains A. And then, so I've taken care of that one, and then for B, that also contains the empty set as a subset. So I'm going to have an arrow up to B from the empty set. Okay, and then I'm not putting A or B above each other because neither of them contains the other as a subset. But when it comes to the next one, AB, so AB does contain both of B and A as subsets. So that's going to go above both of those ones. And then I don't need to draw a line from that down to the empty set because that is taken care of by the transitivity of the Hasse diagram. Okay, so any lines that would be implied by transitivity, you do not have to draw them in the Hasse diagram. In other words, if I can go up from the empty set to B and then all the way up to AB, then I don't need to draw a line directly from the empty set to AB. Okay, so my next one is AC. So I'm going to put that one above A, but not above anything else, since I haven't got C anywhere else yet. That just contains A as a subset. Then for ABC, that is going to contain AC and AB, as well as B and A as subsets. But I can just put that above AB and AC, and then it'll get A and B by transitivity. Okay, and then the last one is going to be ABCD, so that is going to go above ABC. Okay, so if you look at this completed diagram here, you see that if you start at any point and you are able to move up continuously up along a little chain to any other point, then you should be getting larger and larger sets the whole time. So wherever you start at should be a subset of the next place that you're able to move up to. And yeah, that's that one. Okay, so let's do one of these with the divisibility relationship. So we're going to say that A is less than or equal to B if A divides B. Okay, so again, I'm going to start with the one that divides the most other numbers, which is the number 1 that divides all of the other numbers. So I'm going to put 1 at the bottom, and then 98 will be at the top probably. So then let's see, 2. So 1 definitely divides 2, so I'm going to put 2 over there. But then 7, 2 does not divide 7, so 2 and 7 are not comparable under this partial order. So 2 doesn't divide 7, and 7 doesn't divide 2, so neither of them goes above each other. But then 14 does go above both of those, because 2 divides 14 and 7 divides 14. Okay, and then 49. So 49 is divisible by 7, but not by 2 and not by 14, because those are even. So 49 can just go above 7, like this. And then 98, so 98 is actually divisible by 49, and it's also divisible by 2, so it's also divisible by 14. So 98 is going to go right here. I'll put that above 49 and above 14, and then it's also above everything else by transitivity. So that's it. Okay, let's look at the last one. So this one is on ordered pairs, and the ordered pair partial order is going to be when the first coordinate here is less than the first coordinate in the second pair, and the second coordinate in the first pair is less than the second coordinate in the second pair. So you have the less than or equal relationship in both cases for both coordinates. Okay, so let's see, what can I put at the bottom here? I guess I'll start with 0, 1. So let's see, I'm going to put 0, 1 there. Now 1, 0 is not going to be above that, so I guess I'm going to have to put 1, 0 over here to the side. Okay, now 1, 1 should be above both of those because 1 is greater than or equal to 1, and 1 is also greater than or equal to, so if you look at the coordinates here, this first 1 is greater than or equal to the first coordinates of both of the lower points there, and then the second coordinate of 1 is greater than or equal to the second coordinates of both of those points there. And then let's see, 1, 2, and 2, 1. So 1, 2, and 2, 1 are both going to be above 1, 1. But neither of them is above each other. So I guess I'm making like a little X here, like this. So this is going to be 1, 2, and this is going to be 2, 1. It doesn't really matter which order you put them on from left to right. They just both need to be above 1, 1, and neither of them should be above each other. Okay, so that is that. In a certain state, license plates consist of 3 capital letters followed by either 3 or 4 numbers. So part A, how many license plates consist of 3 capital letters followed by 3 numbers? Okay, so there's a couple of things to keep in mind in this problem. You know this is in the part that's called counting with order, so that already tells you that you should count with order. But if you didn't know that, you could figure it out because if you rearrange the letters in a license plate, you get a different license plate, right? So we definitely need to count license plates in different orders as being different outcomes. And that kind of restricts which of the counting rules we're allowed to use. So we could use the multiplication rule. You could potentially use the permutation rule, except that when you're doing permutations, you're not allowed to repeat elements that you're taking from the set. And I think we are allowed to repeat letters and numbers here because it doesn't say that we're not allowed to. So we're saying we care about order, and we can repeat characters. So those two things right there tell me that I have to use the multiplication rule. So I have 6 choices to make in creating this license plate. And I have a number of different options at each stage. So I'm going to put 6 little blanks down, and I'm going to fill those with the number of choices that I have at each part. So for the first character of the license plate, it has to be a letter, and a capital letter. So I have 26 choices there. And then for the next character, it also has to be a letter, a capital letter, and I can use any of the 26 again because I'm allowed to repeat. And so that's going to be the same for the first 3 there. They all have to be letters. And then for the last 3, so those were letters. For the last 3, I have to use numbers. So that's going to be 10 numbers, 10 numbers, 10 numbers. So your choices are 0 through 9. So those are the numbers. And I'm using the multiplication rule to just multiply together the number of choices that I have at each stage of creating the license plate. So you can simplify that if you want to, or you can just kind of leave it like this. I don't really care personally. So I'll just leave mine like that. Okay, how many license plates consist of 3 capital letters followed by 4 numbers? So this is going to be exactly the same, except you have 7 choices, and you're going to have an extra 10 on the end. Maybe I should call these decisions or something instead of choices. I don't know. When I say choices, that makes it sound like the number of options at some stage is 6 or 7. So these things that I'm multiplying together are the number of options for each decision. I'll just put that in parentheses. Okay, so I have 7 decisions, and for my first one I have 26 choices, and then 26 again, and 26 again for each of the letters. And then for the numbers I have 10 choices. Each time I go to put a number I have 10 choices again, because I'm allowed to repeat. Okay, so let's look at part C, or actually I guess I should simplify this a little bit. Okay, now let's look at part C. So how many license plates are possible in total? So in total, they can be 3 letters and 4 numbers, or 3 letters and 3 numbers, and these are mutually disjoint. Or just disjoint, I guess, from each other. So no license plate is in both of those groups. So that tells me that I can use the addition rule. So the addition rule is going to be, I'm just going to add together what I got for it, part A and part B. And so I'm just going to get 26 to the third, 10 to the third, plus 26 to the fourth, 10 to the, oops, that's 26 to the third, right? Sorry, I'm already making mistakes. And then this will be 10 to the fourth. And I'm not going to simplify that, I'll just leave it like that. Okay, and then for the last part, if a license plate is selected at random, what is the probability that it consists of 3 capital letters followed by 3 numbers? Okay, so if we take a license plate from all of the license plates in this state, so our sample space here is what we did in part C. So let me just write that down. So sample space is part C, and then the event that we want the probability of, that is part A. So we're going to do part A divided by part C. Sorry, that looks like an A. Like that. So this is going to be 26 to the third, 10 to the third, divided by 26 to the third, 10 to the third, plus 26 to the third, 10 to the fourth. And then you can put that in a calculator, or you can just leave it just like that. I don't care. Okay, let's look at number 2. In a certain state, license plates consist of 3 capital letters followed by 3 numbers. So part A is how many license plates are possible in total. So this is the same as on the last problem. So I'm going to use the multiplication rule, and I'm going to have 6 little blanks that represent the number of choices that I have at each stage of creating the license plate. So for the first blank, I have 26 choices for the first letter, so that's 26. And then I have 26 choices again for the second letter because I'm allowed to repeat, and then the same for the third letter. And then for my numbers, I have 10 choices for each number, 0 through 9. So these will all be 10. And then you can simplify this if you want to or not. I don't really care either way. Okay, part B, how many license plates have the same first 2 letters? For example, AAH or BBX. Okay, so we're going to do this with the same approach, but the number of choices that we have for our second letter will be different. So I'm going to have 26 choices for my first letter, and then for my third letter I have 26 choices again, and then for the numbers I still have 10, 10, and 10. But what about the second letter there? So the second letter has to match the first letter, so I'm only going to have 1 choice there, because once I've made the once I've made the first letter already, then I have to match the first letter. So this is going to be 1 choice because it must match the first letter. Okay, and then we can simplify this a little bit. Okay, and then part C, how many license plates do not have the same first 2 letters? So this do not part, I'm going to use the difference rule. So what I'm going to do is I'm going to take the total number of license plates, and then I'm going to subtract the number with the same first 2 letters. Okay, and that'll leave me the number that do not have the same first 2 letters. Alright, so this is going to be part A minus part B. So this is going to be 26 to the 3, 10 to the 3, minus 26 to the, minus 26 to, oh my gosh, sorry guys, 26 to the 2 minus 10 to the 3. And then you can simplify that if you want, or you can just leave it like this, that's fine. Okay, part D, if a license plate is selected at random, what is the probability that it has the same first 2 letters? So our sample space here is going to be part A And then the event is part B. So the answer here is going to be B divided by A. So this is going to be 26 squared, 10 cubed, over 26 cubed, 10 cubed. And then you can simplify that if you want to. If you simplify it, it'll become 1 over 26. All right, and that's it. Okay, let's look at number 3. In a certain state, license plates consist of 3 capital letters followed by 3 numbers. So part A is just the same again that we've seen a couple times now. So this is going to be multiplication rule. And then for your first letter, you have 26 choices. For your second letter, you have 26 choices. Third letter, you have 26 choices. And then for your numbers, you have 10 choices for each of them, 0 through 9. And then I'll just simplify it a little bit. Okay, and then now part B is a little bit different. So how many license plates have no repeated characters? Okay, so we have to be a little bit more thoughtful about this one. So for my first letter, it can be anything because I can't repeat with just one letter. But then for my second letter, I have to not repeat the letter that I've already put down. So when I get to the second letter, I have to take away one letter from the alphabet, whatever letter I'd already picked. So I'll only have 25 choices left. And then after that, I have to take away the first 2 letters from my alphabet of choices. So I'm only going to have 24 left. So these here are because we cannot repeat previous choices. Okay, and then when it comes to the numbers, the first one I can do anything, so that'll be 10, but then when it comes to the second one, I can't repeat the first one, so I only have 9 to choose from, and then for the third one, I only have 8 to choose from because I can't do either of the first 2 numbers that I picked. Okay, so that's the same explanation for those 2 right there. And then that's about as simple as it'll get unless you want to actually multiply it out. It's up to you if you want to do that or not. I don't really care either way. It'll just be some ghastly long number. Okay, part C, how many license plates have at least 1 repeated character? Okay, so you have to be careful here and realize that this is the opposite of part B. So let me just write that. This is the opposite or the complement of part B. So at least 1 repeated character means that it doesn't have no repeated characters. Okay, so what we're going to do is the total number of license plates minus the number of plates with no repeated characters. So this is going to be part A minus part B. So that'll be 26 cubed, 10 cubed, minus 26, 25, 24, 10, 9, 8. And I'm just going to leave it like that. I don't think there's a way to simplify that really. Okay, and then in part D, if a license plate is selected at random, what is the probability that it has at least 1 repeated character? Okay, so our sample space here is part A, which is all the license plates. And then the event is part C. Okay, so we're just going to do, we're going to do part C divided by part A. So this is going to be 26 cubed, 10 cubed, minus 26, 25, 24, 10, 9, 8, all divided by part A, which is 26 cubed, 10 cubed. And then you can put that in a calculator if you want, or leave it like that. Okay, number 1, a researcher writes 50 papers in 23 years with a total of 61 co-authors. This is actually pretty fast, I think. Most people write 1 a year or less. But anyway, what is the average number of papers per year? So you're just going to do the total papers divided by the number of years. Okay, so this is just going to be 50 over 23. And that is approximately, using a calculator, that is approximately 2.17. Okay, then part B, there must have been a year when the researcher wrote at least how many papers. So here, this is using the same principle, which was not in the textbook, but I explained in my video lecture, that the average is always between the maximum and the minimum, and the maximum number of papers that in a year that the researcher ever wrote must be an integer, right? So the maximum has to be greater than or equal to the average, and it also has to be an integer. So the maximum has to be at least 3, because that's the smallest integer that is larger than 2.17. So what we're going to do is we're just going to round up 2.17, so we'll round up, and we get 3. Okay, so that's just 3. If you think about it, it also makes sense because if he wrote 2 papers every year for 23 years, he would have only gotten to 46 papers. So there must have been a year when he wrote more than that. All right, let's do part C. What was the average number of co-authors per paper? So we're just going to do this the same way. We're going to do the total co-authors divided by the number of years. Oh, sorry, not the number of years, by the number of papers, right? So this is going to be 61 over 50, and that is exactly 1.22. Okay, and then part D, there must have been a paper with at least how many co-authors? So again, the maximum number of co-authors has to be an integer, and it has to be greater than or equal to 1.22, so it must be at least 2. I mean, he could have written a paper with all 61 of those people. There have been papers with a lot of co-authors. I don't know if there have ever been any with 61, but at least there must have been a paper with at least 2. Because if he'd written them all with just 1, then he wouldn't have gotten to 61. Okay, so what we're doing here is we're just rounding up 1.22, and we're getting 2. Okay, so that's it. It's pretty easy. All right, number 2, a certain college class, which met 42 times in total during a semester, had 20 students. During the semester, a total of 200 absences were recorded. So you can imagine that attendance sheet that I used to pass around having 200 little X's on it. So what was the average number of absences per meeting? So the total absences is going to be divided by the number of meetings. Okay, so this is going to be 200 divided by 42, and that is approximately 4.76. Okay, so part B, there must have been a meeting with at least how many absences? So we're just going to round this 4.76 number, oops, that's not 4. We're just going to round that up because the maximum has to be greater than or equal to the average, and it also has to be an integer, so it must be at least 5. And that's the ceiling notation that I'm using there, in case you forgot that notation, that little, the little arms around the 4.76, that is the ceiling, which means round up. Okay, let me just make a note that you round up. Okay, and then what was the average number of absences per student? So we're going to do the total absences, and then we're going to divide by the number of students. So this is going to be 200 over 20. I don't think I need a calculator for that. That is 10. So I forgot to circle this one. Okay, and then part D, there must have been a student with at least how many absences? Okay, so we're going to do the same thing we've been doing. We're rounding up, but this time we already have an integer, so it's just going to be 10 again. So there must have been a student with at least 10 absences. Since the average has to be greater than or equal to, or sorry, since the maximum has to be greater than or equal to the average, and the maximum also has to be an integer, we can't go any higher than 10 since that's already an integer. Okay, number 3. I was kind of looking around my room when I was writing these questions, and I just spotted the Harry Potter series, so that's where this question came from. There are 7 books in the Harry Potter series, consisting of 4,224 pages and 1,084,170 words, according to Google, anyway. What is the average number of pages per book? Okay, so we're just going to do the total pages, and we're going to divide by the number of books. And so that's going to be 4224 divided by 7, which is approximately 603.4. Oh, that's quite a lot. There must be a book with at least how many pages? Okay, so the maximum has to be at least as large as the average. So we're just going to round the average up to the nearest integer that is above it. and that is going to give us 604. So I'm rounding up. Okay, don't round down, round up. And then part C, what is the average number of words per book? Okay, so we're going to take the total words and we're going to divide by the number of books. Could have also done average words per page. That might have been interesting. Okay, so this is going to be 1,084,170 divided by 7, which is approximately 154,881.4. Okay, and then part D, there must have been a book with at least how many words? So we're going to take our last answer and we're just going to round that up, since the maximum has to be greater than or equal to the average, and it has to be an integer. So the least integer that is greater than the average is 154,882. So there must have been a book in the series with at least that many words. I'll give you a hint. Definitely the last book. That one was long. Okay, that's it. Okay, so we have to use the binomial theorem to expand each polynomial. And let me just remind you what the binomial theorem says. So it says a plus b to the n is equal to the following sum from k equals 0 to n of n choose k, a to the n minus k, b to the k. This one I have memorized because it's quite useful. Okay, so that is your formula, the binomial theorem. All right, so in this case, a is 2x, so that's a, and then y squared is b, and then 6 is n. All right, so those are the things that you need to use in this formula. So we're going to get that this is going to be the sum from k equals 0 to 6. So I'm putting 6 in for n. And then it's going to be 6 choose k. And then we're going to have a. Be careful to put a in parentheses. Okay, so 2x is in parentheses, so it all gets this exponent. Oops, the n is going to be 6. Sorry. So this will be 6 minus k. And then b, put that in parentheses as well. Okay, and then this is going to be to the k. Okay, so now that you have all that in, and the only variables left are x, y, and k, go ahead and expand the summation, and then at the end we'll simplify it. So first I'm going to plug in k equals 0, so this will be 6 choose 0, 2x to the 6 minus 0, y squared to the 0, and then I'm plugging in 1 for k, so 6 choose 1, 2x to the 6 minus 1, y squared to the 1. All right, I'll come back down to the next line, and then plus 6 choose 2, 2x to the 6 minus 2, y squared to the 2, 6 choose 3, 2x to the 6 minus 3, y squared to the 3. You just keep going like this until you get to 6. It's kind of boring. You can fast forward if you want. Okay, and now you have to simplify it a little bit more. So I'm going to look up what all of those combinations are, and then I'm also going to be using some rules of exponents and things to also simplify the 2x part being raised to an exponent. So like you have to raise the 2 to the exponent, you also have to raise the x to the exponent, and then when you have y squared to another exponent, you're going to multiply those two exponents together. Okay? Alright, so 6 choose 0 is 1, and then we have 2x to the 6, so this is going to be 2 to the 6 and then x to the 6, and then we have y squared to the 0, so that's just going to be 1. Then 6 choose 1 is 6, and then we have 2 to the 5th and x to the 5th, and then we have y squared to the 1, so that's y squared. And then 6 choose 2 is 15. I'm actually just looking at Pascal's triangle to do that. And then this is 2 to the 4th, x to the 4th, and then y to the 4th as well. So 2 times 2, 4. And then we have 6 choose 3, which is 20, and then 2 to the 3, x to the 3, and then y is going to be to the 6th. and then we have 6 choose 4, which is going to be 15 again, and then 2 to the 2, x to the 2, and then y is going to be to the 8th, and then we have 6 choose 5, which is 6 again, and then we have 2 to the 1, x to the 1, so I guess I don't need to write that, and then we have y to the 10th, and then finally 6 choose 6 is 1, and then we have 2x to the 0, so I don't need to write that, because that's 1, and then y to the 12th. Okay, and then I'm just going to multiply some of these together and do the powers on the 2's. Okay, so this is going to be 64x to the 6th plus 192 x to the 5th y squared plus 240 x to the 4th y to the 4th plus 160 x cubed y to the 6th plus 60 x squared y to the 8th plus 12x y to the 10th, and then finally just y to the 12th. And that is the final answer there with complete simplifications. All right. Okay, so we're going to expand another one with the binomial theorem. So let me just remind you what the binomial theorem says. A plus b to the n is the sum from k equals 0 to n of n choose k times a to the n minus k, b to the k. All right, so we're going to apply that to this by making a into 3x, and then negative y, make sure you get the negative there, is going to be b, and then 5 is going to be n. So if we use this formula, then we get the sum from k equals 0 to 5 of 5 choose k times 3x. Make sure you put that 3x in parentheses so it all gets the exponent. So this will be, sorry, that's not any character. 5 minus k exponent there, and then make sure you put the negative in with the y, and that'll be to the k. Alright, so then we're going to expand this by just plugging in all the values for k from 0 to 5. So this will be 5 choose 0, 3x to the 5 minus 0, negative y to the 0, and then 5 choose 1, 3x to the 5 minus 1, negative y to the 1, and then 5 choose 2, 3x to the 2, negative y. Sorry, I did that wrong, didn't I? This should be 5 minus 2 there, and then this one is to the 2. Okay, and then 5 choose 3, 3x to the 5 minus 3, and then negative y to the 3, and then 5 choose 4, 3x to the 5 minus 4, and then negative y to the 4, and then finally 5 choose 5, 3x to the 5 minus 5, and then negative y to the 5. Okay, and so from here I just need to simplify all of this. So I'm going to simplify the exponents. I'm going to apply each exponent separately to the 3 and to the x. And then also for negative y, I'm going to do negative y raised to each power, so I'll do the negative and the y part separately. And then I need to simplify all of these choose expressions using either Wolfram Alpha or calculator or Pascal's triangle to figure out what they all are. Okay, so I'm going to come through and do that. So 5 choose 0 is 1, and then I'm going to have 3 to the 5, and then x to the 5, and then negative y to the 0 is just 1, so I don't need to write that. 5 choose 1 is 5, and then I'm going to have 3 to the 4, and then x to the 4, and then I'm going to have negative y, and that's just the 1, so I don't need to write that. And then 5 choose 2 is 10, and then I'm going to have 3 to the 3, and then I'm going to have x to the 3, and then negative y squared is just positive y squared. Okay, then 5 choose 3 is 10 again, and then I have 3 squared, and then x squared, and then negative y cubed is the same as writing it like this, so it just has the negative once there. Okay, and then 5 choose 4 is 5 again, and then I have 3, and then I have x, just to the 1 power each, and then negative y to the 4th is the same as y to the 4th. And then finally 5 choose 5 is 1, and then 3x to the 0 is also 1, and then I have negative y to the fifth, which I can write with just one negative like that. Okay, and then I just need to make another pass through there again and multiply all the coefficients together, put the negatives in front. So when I do that, I get 243 x to the fifth minus 405 x to the fourth y, and then 270 x cubed y squared, and then minus 90 x squared y cubed, and then plus 15 x y to the fourth, and then finally minus y to the fifth. And that is the whole final answer there. Okay, let's look at number 3. So again, I'm going to use the binomial theorem. So let me, oops, that's the wrong side. Let me write what that is. So a plus b raised to the n is equal to the sum from k equals 0 to n of n choose k, a to the n minus k, b to the k. So in this case, my a is x, and then my b is 2y squared, and then my n is 4. Okay, so let's go ahead and use the formula. So this will be the sum from k equals 0 to 4 of 4 choose k times x to the n minus k, and then make sure you put the 2y squared part in parentheses for b, and then that's going to be to the k. Okay, so let's go ahead and do this sum. I'm going to plug in all the values for k from 0 to 4. So the first will be 4 choose 0, x to the, oops, I think this should have been a 4 right here, right? That should have been a 4. So x to the 4 minus 0, and then 2y squared to the 0, plus 4 choose 1, x to the 4 minus 1, 2y squared to the 1, plus 4 choose 2, x to the 4 minus 2, 2y squared to the 2, and then the last two terms, 4 choose 3, oops, and then x to the 4 minus 3, and then 2y squared to the 3, and the last term, 4 choose 4, x to the 4 minus 4, 2y squared to the 4. All right, and now I just need to simplify all of these exponents and coefficients, distribute the exponents, figure out what these choose expressions stand for. So 4 choose 0 is 1, and then we have x to the 4th, and then 2y squared to the 0 is also 1, so I'm not going to write that part. And then 4 choose 1 is 4, and then we have x cubed, and then we have 2y squared just to the 1 power. Okay, then 4 choose 2, that is 6, and then we have x squared, and then we have 2y squared, so that's the square, sorry, 2y squared squared. So the square is going to come down and be on the 2 there, and then y is going to be to the 4th power, because we multiply the exponents together. All right, then 4 choose 3 is 4, and then we have x to the 1, and then we have 2y squared cubed, so the cube power is going to go on the 2, and it's also going to go on y squared to make y to the 6th. And then 4 choose 4 is 1, and then x to the 0 is also 1, and then we have 2y squared to the 4th, so the 2 gets the 4th power, and then the y squared also gets the 4th power and becomes 8. All right, and then we just need to simplify a little bit everything again. So this will be x to the 4th, and then this will be 8x cubed y squared, and then 24x squared y to the 4th, and then 32x y to the 6th, and then 16y to the 8th. And that's it. Okay, number 1. So we're going to answer the questions for this graph. So the first question is the graph simple? So a simple graph is one that has no parallel edges and no loops, so this is not simple. So the answer is no, it has parallel edges. For example, E2 and E4, as well as E6 and E7. You don't have to put that much detail in your answers, but that's just so you understand. Part B is the graph connected. So yes, it is connected, and the reason there is because we can reach any vertex from any other vertex by walking along edges. Maybe I should say, oh, I left out the word reach. I should have used the word walk anyway, since that's the technical term that we learned. So we can walk from any vertex to any other vertex. Okay, what is the total degree of the graph? So I'm just going to go around all the vertices and add up their degree. So this one has 2 little edges coming out, so that's 2. This one has 4 edges coming out, so that's 4. This one also has 4, and then this one has 2, and this one has 4. Okay, so that is going to be a total of 16. So I'll just write down my calculations here. All right, does the graph have an Eulerian circuit? If so, list it. So an Eulerian circuit is one where you visit every vertex and you visit every edge, and you cannot repeat edges, but you can repeat vertices. So let me see if I can find one by going around this graph. Let's see. So if I start, oh, actually there's a way to test for this, isn't there? So if every vertex has an even degree, then there should be one. So let me write that down. So every vertex has an even degree. So yes. All right, and now let's try to find one. So maybe I can just go around the outside first. And then if I go back down here and then I come back up, then I think I'm starting and stopping at the same point, which is something that you have to do. So let me write that down. So I'm going to start at V2 and go along E1 to V1, and then along E8 to V4, and then along E5 to V3, and then along E4 back to V2. And then I'm going to go down E2 to V5, and then I'm going to go down along E7 to V4, and then I'm going to come back up E6 to V5, and then I'm going to come back up E3 to V2. Okay, so I started and stopped at the same point, and I went through every edge exactly once, so that is an Eulerian circuit. All right, does this graph have a Hamiltonian circuit? If so, list it. Okay, so a Hamiltonian circuit, first of all, it has to be a simple circuit, so we cannot repeat any edges, and we cannot repeat any vertices, but we do have to visit every vertex once. So you want to look at the vertices, first of all, that have degree 2. There's only one way to enter and exit from those vertices. So if I want to get to V1, I have to enter and exit through those 2 edges that I just highlighted. And it's the same deal with V3. So I have to enter and exit V3 through those 2 edges. But then once I've done those 4 edges, I can't add anything to this because that would require me to visit some vertex more than once, because I would have already visited all 4 of these vertices, and then there's no way for me to get to V5. Okay, so this one does not have a Hamiltonian circuit, and I'm not asking you to explain why it does or doesn't, just to answer the question. So, but I'll just put an explanation in parentheses here for your sake. So we have to enter and exit E1 through E1 and E8, and we have to enter and exit V3 through E4 and E5, but once we have those 4 edges, we can't add anything else. let's look at part 2. Is the graph simple? So this graph has a loop and it has two parallel edges, so it is not simple. So I'll just write that down. So the parallel edges are E2 and E3, and it also has a loop, which is E6. Is the graph connected? Yes, it is connected. I can walk from any vertex to any other vertex along a series of edges. So when you're taking the test, you don't have to write these explanations, but I'm just doing them so you'll understand. What is the total degree of the graph? So let me go around and check all the vertices. So this one has 1, this has 1, 2, 3, 4, this has 1, 2, 3, 4, 5, this one has 2, this has 1, 2, 3, 4, 5, this has 1, 2, 3. Okay, so the total degree is 1 plus 4 plus 5 plus 2 plus 3 plus 5, so that should be 20. All right, and then does the graph have an Eulerian circuit? So it's not going to have one because of what we discussed previously, that there's a test, which is whether all the vertices have odd degree. So no, because not all the vertices have even degree. So they all have to have even degree in order to have an Eulerian circuit. Does the graph have a Hamiltonian circuit? If so, list it. So this is a circuit by which you could visit every vertex exactly once. So you cannot repeat edges, and you also cannot repeat vertices. So the answer here is going to be no, and I'm focusing on this V0 part to see that the answer is no. So we can't visit V0 without repeating an edge, so we would have to repeat E1, and that would not then be a Hamiltonian circuit. All right, let's look at the third one here. Is the graph simple? So in this case, it is simple because there are no repeated there are no parallel edges and there are no loops. Now, is the graph connected? So in this case, you might be a little bit fooled if you just glance at it, but it is actually not connected. So it's two completely separate triangles, and there are no vertices where those triangles are crossing at, so you cannot get from one triangle to the other triangle along an edge. So it's two disconnected triangles. Okay, so for example, you cannot get from vertex U to vertex Z along any sequence of edges. What is the total degree of the graph? So I believe it's 6 vertices and they all have degree 2. So this is going to be 12. Does the graph have an Eulerian circuit? So the answer is going to be no, because it's disconnected. So you can't visit every edge along a single circuit because it's disconnected. And then the same with the Hamiltonian, it's going to be no, for the exact same reason. We can't visit all the vertices in one visit, or in one circuit. Okay,